Hello friends, we can discuss the theorem 3.11, that is, let V be an n-dimensional vector space over the field F and W is an m-dimensional vector space over F. Let script B be an ordered basis for V and script B dash be an ordered basis for W. Then the theorem says that for each linear transformation T from V into W, there is an m by n matrix A with entries in F such that matrix T alpha related to the basis B dash is equal to A into matrix alpha related to the basis B. That is, we have to prove for each linear transformation there is a matrix A and it is true for every vector alpha in V. After proving this, we have to show furthermore T to A is a 1-1 correspondence between set of all linear transformation from V into W and set of all m by n matrices over the field F. That is, the set of all linear transformation from V into W and set of all m by n matrices over the field F is 1, 1 and onto. To proving this, let B is equal to set alpha 1, alpha 2, etc. alpha n be an ordered basis for V and script B dash is equal to set beta 1, beta 2, etc. beta n be an ordered basis for W and T be a linear transformation from V to W. Then for each alpha j belongs to script B, we know that T of alpha j belongs to W because script B is an ordered basis for W, which implies that T of alpha j is a linear combination of beta 1, beta 2, etc. beta m. Since beta 1, beta 2, etc. beta m is an ordered basis, the representation of T alpha j in terms of beta 1, beta 2, etc. beta m is unique. Suppose there exist unique scalars a1j, a2j, etc. amj. Then we can represent T of alpha j as a1j beta 1 plus a2j beta 2 plus etc. plus amj beta m, which is equal to sigma I equal to 1 to m aij beta I. We can denote this as equation 1. Now let alpha belongs to V. Then there exist unique scalars x1, x2, etc. xn, since script B is an ordered basis for V, such that alpha is equal to x1 alpha 1 plus x2 alpha 2 plus etc. plus xn alpha n. Since alpha 1 alpha 2 etc. alpha n is an ordered basis, this representation is unique. The coordinates of alpha with respect to the basis B is a coefficient of alpha 1, alpha 2, etc. alpha n. Therefore, coordinates of alpha with respect to the basis B is equal to matrix x1, x2, etc. xn. If alpha is equal to x1 alpha 1 plus x2 alpha 2 plus etc. xn alpha n, T of alpha is equal to T of x1 alpha 1 plus x2 alpha 2 plus etc. plus xn alpha n. Since T is linear, we can write x1 into T alpha 1 plus x2 into T alpha 2 plus etc. plus xn into T alpha n. That is sigma j equal to 1 to n xj T alpha j. From equation 1, we will get the value of T alpha j, that is sigma I equal to 1 to m aij beta I. We can substitute the value of T alpha j here, then we will get sigma j equal to 1 to n xj into sigma j equal to 1 to m aij beta I. And interchanging the summation, finally we will get sigma I equal to 1 to m sigma j equal to 1 to n aij xj beta I. If we provide 1 to etc. m to I, we will get T of alpha is equal to sigma j equal to 1 to n a1j xj beta 1 plus sigma j equal to 1 to n a2j xj beta 2 plus etc. plus sigma j equal to 1 to n amj xj beta. The coordinate matrix of T alpha with respect to the script B dash is coefficient of beta 1, beta 2, etc. beta. That is, coordinate matrix T alpha related to the basis B dash is equal to matrix sigma j equal to 1 to n a1j xj, sigma j equal to 1 to n a2j xj, etc. sigma j equal to 1 to n amj xj. When we provide the value 1 to etc. n to j, we will get a11 x1 plus a12 x2 plus etc. plus a1n xn, a21 x1 plus a22 x2 plus etc. plus a2n xn, etc. am1 x1 plus am2 x2 etc. plus amn xn. which is same as matrix A11, A12, etc. A1n, A21, A22, etc. A2n, etc. AM1, AM2, etc. AMN into matrix X1, X2, etc. Xn. Now we get coordinate matrix T alpha related to the basis B dash is equal to A into coordinate matrix alpha related to the basis B. So we have proved that for each linear transformation there is an m by n matrix A. So now we have to prove the set of all linear transformation from V into W and set of all m by n matrices over the field F is 1, 1 and on 2. For that, take T belongs to LV of W. LV of W is a set of all linear transformation. And define a function g from LV of W to F m by n matrix. Since g is a function and T is a linear transformation, g of T will be a matrix A. Then by representation of matrices, we will get A is unique. Since A is unique, T is well defined and G is 1 to 1. Now we get G is 1 to 1. Now we have to prove G is onto. For that, take A belongs to F m by n matrix. Since A is a matrix, we can represent A as Aij into m by n. Let alpha belongs to V. And we know that script B is a basis for V. There exist unique scalars x1, x2, etc. xn in F such that alpha is equal to x1 alpha 1 plus x2 alpha 2 plus etc. xn alpha n. Since T is linear, we can represent T alpha is equal to summation j equal to 1 to n a1j xj beta 1 plus x etc. Then we since T belongs to LV of W and we have already proved coordinate matrix T alpha related to the basis B dash is equal to A into coordinate matrix alpha related to the basis B. Then we will get G of T is equal to A. Thus we get G is onto. We have proved G is 1, 1 and G is onto. So the set of all linear transformation from V into W and set of all m by n matrices over the field F is 1, 1 and onto. Thank you.